In this video lecture, we're going to lay the groundwork for understanding how generators work and how power transformers work. Power transformers and electrical generators are important parts of the electrical distribution network that brings electrical power to most homes, businesses, government buildings, etc. in our society. And this entire topic relies on the concept of electromagnetic induction. I'd like you to think back to the beginning of the semester when we were talking about electric charge moving around in conducting surfaces, especially due to the proximity of a charged object. I said it was possible to induce a net charge in an object, and to induce specifically means that the two objects do not come into contact. There is no direct conduction of charge from one object to another. To induce meant to cause a change, but without touching, strictly by field interactions. Similarly, electromagnetic induction will take advantage of the relationship between magnetic fields and charged particles to push charges around through wires due to the proximity of a magnetic field and relative motion between that field and the conducting wire. An electrical current can be induced in a wire if that wire is in a magnetic field and either a magnet is moving near a stationary wire or a wire is moving in a constant magnetic field, or a magnetic field is changing while the wire is in it. We will specifically talk about the first two. The big idea that we're trying to get at here is that these are devices that convert mechanical energy into electrical energy. Motors and generators operate on the same principles. Each is a device that transforms energy. A motor transforms energy from electrical into mechanical, and a generator transforms energy from mechanical into electrical, using the exact same setup. A motor is what we talked about in the previous video, where electrical current passes through a magnetic field and therefore experiences a force, and if arranged properly, this conductor spins. This could be a wheel or a fan or a pump or whatever. A generator is the same basic setup, but it is arranged so that the loop of conductor spins for other reasons. Something mechanical like a windmill or a water wheel, or because you grabbed a crank and turned it by hand. You provide the motion to this loop, and now every atom in this loop is an atom that is moving through a magnetic field. So for example, you could do the right-hand rule on this piece of wire in this loop as that piece of wire moves up. All of the positive charges in the atoms in that wire are moving upward in that moment through a magnetic field that you can see drawn as yellow arrows pointing to the right on our screen. If you use the right-hand rule, you should be able to determine that every positive charge in that piece of wire is experiencing a force into the page, as represented by this white arrow. However, on the other side, over by the north, you would see the other side of the loop is at the same time moving down. So if you right-hand rule on all of the positive charges in the atoms on that side, you would see that they all experience a push along the wire in this direction. So what we have here as this loop spins in this magnetic field is that the positive charge is pushed along the length of wire because of that magnetic field, shoving charges all throughout the wire like this, and therefore lighting up whatever it is attached to. In other words, we've created an electrical circuit. This whole device is your EMF for the circuit. For some situations, like the one shown here, the way that I just did the right-hand rule on the previous slide is not as effective for figuring out what direction the current will flow. And so for a situation like this one, we'll use something called Lenz's law. That is Lenz, the Russian surname, not lenses like optical glass instruments. Lenz's law tells us that in any particular coil or loop that has a magnetic field passing through the inside of it, if the amount of magnetic field passing through the loop changes, a current will be induced in the coil in whichever direction would oppose that change. So movement of a magnet relative to a coil will produce a current in the loop, which means it's also producing an EMF to cause the current to move. For example, here we have a coil of wire, and we have a magnet that is raised upward. You can see the little cartoon motion showing that this magnet is moving upward. As it moves upward, more and more of its magnetic field is pointing through the loop. Imagine this magnet starting way down here and moving up. As it moves up, more and more of its magnetic field is passing through that loop. That's a change. To resist that change, a magnetic field is generated around the loop that points the other way. That's not shown in this drawing. But the coil generates a current passing clockwise through this wire that will, by the right-hand rule 2, make a magnetic field pointed down inside the loop to resist the change that was caused by the magnet being brought closer. Go ahead and right-hand rule 2 on the loop to verify that the current that is shown on this drawing will make a B field that is pointed down on the inside of the coil. This only happens for as long as there is motion between the magnet and the coil. If there's no motion, then there's no change in the amount of B field through the loop, so the loop does not have an induced current to resist it. In this drawing, as the magnet is pulled down, less and less of the magnetic field will be pointed through the loop. A B field is therefore generated around the loop to reinforce the B field that is getting weaker and weaker. As you move the magnet away, a current will pass through this coil counterclockwise in order to reinforce that weakening magnetic field due to you pulling the magnet farther and farther away. There are some tricks to keep track of. For example, which end of the magnet you're looking at. Definitely draw the B field for your bar magnet if it's not given to you. As this particular magnet is moved up, the amount of magnetic field passing through the loop increases and a current is induced in whichever direction would fight against more and more of the B field pointing down here. That means counterclockwise current to make a B field pointed up inside the loop. This is the same as in situation A, but because the magnet has been flipped over, we get a current in the opposite direction. And similarly, with the south of the magnet pointed upward, but the magnet being moved downward, less and less of the magnetic field passing through the coil as the magnet moves away. So a current is induced in the coil to create more magnetic field passing down through the coil. Whichever direction you're moving the magnet, the current will be induced to oppose the change in the magnetic field passing through the inside of the coil. And then if there's no motion, everything's going to be all right. No motion, no I. So with Lenz's law, what realistically could we be asked? Well, a question like this one would be a good one. Given the setup shown here, as the bar is pulled to the right by some external force, like say me, what direction will the induced current through the resistor be? The resistor is not moving through the magnetic field, but it is connected by conducting wire, presumably, here, and this bar that's moving is a conductor, and this is all conductor. As the bar is pulled to the right, you could do the right-hand rule on it on any given positive charge in the middle of the bar, any part of any atom in that bar. As the B field is pointed into the screen, and all of the positive charges in the atoms of that bar are moving to the right, you should be able to determine that they will experience a Lenz force pointed up the page. If that positive charge is getting pushed up the page, and nothing is happening to the positive charges here, here, and here, then the positive charges that are getting pushed up the page in the moving bar will actually cause the rest of the charges to move throughout that circuit. You will get a counterclockwise current passing through the moving bar and all of the wire that is from the moving bar through the resistor, through the ammeter, back to the moving bar again. Counterclockwise current. That same question could be answered a slightly different way, which is with Lenz's law. As the bar moves more and more to the right, more and more magnetic field pointed into the page is introduced inside of the loop. As the bar moves to the right, bringing more and more magnetic field pointing into the page, a current will be induced in the loop to resist that change. The current that would resist that change would have to make a magnetic field pointed out of the page to fight the fact that you were putting more and more and more magnetic field pointing into the page by moving the bar to the right. What direction would the current flow to make a magnetic field pointing out of the page? Well, it's either counterclockwise or clockwise. So put your right hand on any part of this loop and determine how you get a magnetic field pointed out of the page inside the loop. And you get the same answer. Again, I want to emphasize the fact that current is flowing means there must be some EMF making it flow. A voltage source, but there is no battery. The magnitude of the EMF is equal to the magnetic field B times L, the length of the moving object, times V, the speed at which the object is moving. So as we move this bar to the right, L would be the length from here to here, and V would be how fast I pulled it this way. That would generate an EMF, and I would know which end of the bar is positive and which one is negative by determining with the right-hand rule which direction the current is flowing. In this case, I would not first determine positive and negative and therefore know the direction of current, as we did with the battery. In this case, I would use the right-hand rule to determine the direction of the induced charge flow, and that would be able to let me back determine which end of the rod must have been a positive and which one must have been a negative in terms of EMF. Again, as this drawing is showing, there are two ways that you can determine the direction of the current flow. You can use what OpenStax refers to as right-hand rule 1, which is the first way I did it, showing that all of the positive charges in this bar are positive charges moving through a magnetic field, and therefore they are being forced this way, which will cause a counterclockwise current throughout this entire circuit. Or you could have said, by Lenz's law, that as this bar moves farther and farther to the right, more and more magnetic field pointing into the page is introduced on the inside of this loop. Therefore, a current must be induced in this direction, causing a magnetic field that resists that by pointing out of the loop. Either one gives you the same answer. So to recap, this slide, which I will make sure is in your notes, has some problem-solving strategies. This is directly out of the OpenStax textbook, and we've introduced one new equation, which is that when we are inducing a current by moving a part of a loop through a magnetic field, as in the example we just did, the magnitude of the EMF is equal to BLV, where B is the magnetic field, L is the length of the moving piece of conducting material, and V is the speed at which the conducting material is moving. Okay, that's how Lenz's law works, and that's an introduction to electromagnetic induction. I'd like to talk a little bit about how transformers work. I'm not 100% sure that we'll have time to get into it as much as I'd like to. Generators and transformers are a fascinating topic. There's a lot that you can learn there, and we probably won't have time to do as much with them as I'd like to, but I'd like to at least touch on them in a future video or in class.